Hi everyone, so in this new video I will talk about printed antenna arrays. Okay, so the arts and challenges in designing of printed antenna arrays are microstrip antenna arrays. Okay, so what does it mean antenna arrays? How we can differentiate between two type of antenna arrays, what different geometry that we can find in literature. Okay, so in this video I will talk about all this. Okay, so in this presentation we have two principal acts. So the first act I will talk about arts of antenna arrays. Okay, the arts of geometries, and in the second axis I will talk about challenges design. So antenna array, what does mean antenna array? So here when we talk about antenna array or array antennas, so here is a set of multiple connected antennas, okay, like this figure, a set of multiple connected antennas which work together to transmit or receive radio waves. Okay, so here we have several geometries like triangular, here or the rectangular or circles. So we have more than one antenna. Okay, so here we can talk about antenna array. We have more than one antenna in a single geometry. Okay, so in antenna array, several single antennas separated from each other. Okay, like figures here. So separated from each other are geometrically arranged to give desired radiation characteristics that are not possible to achieve with a single antenna. So the question that we can put, why we use them. So here we have two cases. Okay, why we use this antenna arrays, why we use antenna arrays instead of single antenna element. So we have two cases. Okay, see, so the first case, when we talk about high radiation performance, for me I search for high radiation performance, so here I talk about gain and directivity. And the second case, when I talk about smart beam steering. Okay, so here I talk about intelligent or smart arrays antennas. Okay, so the first, high radiation performance. So how we can differentiate between the first tape and the second tape? So for the first tape, when I have one single pulse of excitation used to power on multiple antennas, so here I can talk about the first step, high radiation performance. Okay, so I have one single pulse of excitation used to power a lot of antennas, multiple antennas. Okay, so like figure 1 or figure 2, we have one single linear here. Figure 1, linear antennas, linear array antennas excited or powered by one single pulse. Okay, so with a single feed line. Okay, so here I have one single pulse of excitation. So the same for the figure 2, we have planar array antennas with one single pulse of excitation used to power all antenna elements. So here also I talk about high radiation performance. Why? Because I have just one single pulse of excitation used to power our antenna elements. Okay, so here this figure can explain us why we use array antenna instead of a single antenna. So for the figure A, so we have one single antenna with they equal 3 decibels. Okay, so this single element cannot cover the region here, for example for plane or aircraft application. So this antenna cannot cover this region, so I need to use array antenna with high directivity. So the figure B represents array antennas with 6 elements. So in this array I have a directivity of 80 decibel. Okay, so we have one main beam toward the desired direction toward our plane, and we have secondary lobes. So the main beam has a high level radiation and secondary lobes with lower levels. Okay, so here I talk about high radiation performance. So for example, here we have array antennas with 80 dB used to cover regions of plane or aircraft applications. Okay, so we have other parameters is half power beamwidth is used a lot of in array antennas. So to know how much or how more our antenna is directive. Okay, so we talk about half power beamwidth. So how we can, so this parameter is in degrees. Okay, so how we can determine this parameter. So we take the main beam of our array antennas, a red color for example here. So we take the maximum of radiation and we pass with 130 decibel. So the intersection of our main beam with 130 decibel give us the angle of our half power beamwidth. So more this angle is small, more our array antenna is directive. Okay, so if we have two array antennas with half power beamwidth, to know how of these antennas is more directive, so the array antenna is more directive is the array antenna that has half power, small half power beamwidth. Okay, so this parameter is very important in array antennas. We talk about half power beamwidth. So for the second case, smart beam steering. So for the first case, we talk about high radiation performance, and I say that if we have one single pulse of excitation used to power a lot of or multiple antennas, so we talk about high radiation performance. For smart beam steering, so we have other case. So if we have more than one pulse of excitation used to multiple antennas, so I used a lot of pulse of excitation to power a lot of antennas. So in this example I talk about smart beam steering. Okay, so for example here figure 4 represents hybrid coupler with two input port and two output ports. So figure 5 represents Butler matrix. So here we have 4 input ports and 4 output ports. These outputs are connected to 4 patch antenna elements. Okay, so here we talk about smart beam steering because we have more than one pulse of excitation used to power more than one antenna. Okay, so to understand the principle of this matrix Butler, so I give this example in figure 6. So radiation pattern in Butler matrix 4 multiply 4. So I have 4 inputs and 4 outputs are connected to 4 antenna elements. So if I exceed the first port, what happened here? So I can observe that I have one single beam directed toward desired direction 1. Okay, so if I exceed the second part, so I can observe that I have another main beam toward the desired direction 2, and for 3 output 3, and for the input 4 I have the direction 4 in output. So if I exceed the fourth port, so here I can obtain in output 4 main beam. Okay, each beam is directed toward desired direction. So here I talk about 4 beam with the same level radiation performance. Okay, so here I cannot talk about main beam with secondary lobes, but I talk about 4 beam with the same level. Okay, so now I will talk about antenna arrays, geometries, and the method used to feed in these arrays antennas. So when we talk about linear patch array antennas, so here in figure 7 we have single array antenna serial in serial feeding. Okay, so linear feed array antenna with single pulse of excitation. In figure 8 we have parallel feeding array antenna. So if we observe between these two arrays, the first we have the radiating element in serial distribution. So the alimentation or power is used by one single feed line, okay, between antennas elements. Okay, in figure 8 we have four elements, so the distance between input of each element and input power of excitation, so it's the same for the four antennas. So the distance between the first element and the pulse of excitation equal the distance between the second element and and the parts of excitation, and the third and the fourth and the parts of excitation. So the distance between the parts of excitation and antenna element is the same for the four antennas. Okay, in figure 8, but in figure 7, so the first element is the near to part of excitation, and the second is nearer than the third, and like that. Okay, so the difference between these two types. So for serial feeding figure 7, so when I change frequency in input ports, so the phase shift between radiating elements change. Okay, so here if I change the frequency in input port, the phase shift between radiating elements change also. Okay, but for parallel feeding, when I change frequency, the phase shift between radiating elements stay stable. Okay, we cannot observe change in phase shifts between radiating elements. Okay, so this is the difference between serial feeding and parallel feeding. When I change frequency in input ports for serial feeding, the phase shifts between radiating elements change, but for parallel feeding we cannot observe a change in phase shifts. Okay, so here we have two types of linear patch array antennas. The second case I talk about planar patch array antennas. So if we observe figures 9 and 10, so we have two types. So the first figure we have serial feeding because we use just one single feed line to power all antenna elements. But for figure 10, we have one pulse of excitation and multiple feed lines used to power all antenna elements. So when observe the distance between all antenna elements and parts of excitation, we can conclude that the distance between antenna elements and parts of excitation is the same for all antennas. Okay, so it's the same principle when I change frequency in inputs for serial feeding. The phase shift change between antenna elements, okay, for serial feeding, but for parallel feeding, when I change frequency, the phase shift stays stable for all antenna elements. The last geometry, so I talk here about popular geometries. Okay, so the last geometry is circular patch array antenna. So in figure 11 we have serial feeding. Okay, so the first element feeding is at alright. Okay, and we have in figure 12 parallel feeding. Okay, so the excitation is the center of our array antennas. Okay, so we have two geometries, serial feeding and parallel feeding. So when I change frequency in serial feeding, I can observe a change in phase shifts between antenna elements, but for parallel feeding I can not observe any change in phase shifts between antenna elements. So in this second axis, I will talk about challenges design. Okay, So when I talk about challenge design, we have a lot of case. Okay, so the first case I talk about compact and low profile. So here we talk about size and dimensions of our array antennas. Okay, so we search to have a miniaturized array antennas. Okay, or miniaturization in terms of dimensions. So we have a method used for horizontal antennas that function for wideband or ultra wideband characteristic. So here, for example, if I work for C-band, for example, I take just an example. I work for C-band between 4 gigahertz and 8 gigahertz. So here, to conserve my array antenna, I want to fix a frequency because our parameters in width and length of our array antenna or our has relation with the frequency. So more frequency increase, more the dimensions of our antenna decrease. Okay, so here I want to choose the high frequency to conserve my array antenna. Why? Because more frequency increase, more dimensions of our array antenna decrease. Okay, so if I work in C-band, I want to conserve my array antenna for 8 gigahertz. So if I conceive my array antenna in 8 gigahertz, so I can obtain the small structure for this band. Okay, so always you need to work with high frequency to obtain a miniaturization for your array antennas. Okay, so the second case I talk about high radiation performance. So here I talk about gain and directivity. So more our antenna or our array antenna has high directivity and gain, so our array antenna is better than other antenna that has a small or lower gain and directivity. The third case I talk about low material coupling. So here I can put another video just for material coupling. The methods or techniques are used in literature to decrease material coupling between radiating elements and horizon antennas. So in literature we have three popular methods are ABG structures or electromagnetic band gap structures, and we have also DGS structures or defected ground plane. Okay, so we have civil geometry in ground plane, and we have the third case we can talk about split ring resonator. Okay, so we have three popular methods are used to decrease mutual coupling between radiating elements in arrays antennas, branched arrays antennas, patch antennas, or microstrip antennas, or coupler antennas. Okay, so I can put another video just for this method for this problematic of mutual coupling. So as I see, we need to have a low mutual coupling in our array antennas. Okay, a low mutual coupling. This is a challenge in designing of branched array antennas. The fourth parameter we can talk about flexibility. So here we search to integrate our antennas in any structures, any circuit in industry. Okay, so I talk about flexibility of our array antennas. I can talk about configuration and orientation. So about configuration, if I have array antennas that function for a multiple resonance frequency, for example 4 or 5 frequency is more than one frequency is better than antenna that or array antennas that function for just one single frequency. Okay, so multiple frequency is better than array antenna that function just for one resonance frequency. So orientation, I talk here about beam steering intelligent radiation. I can direct my beam steering toward the desired direction. So I talk about intelligent radiation. Okay, orientation of our beam toward the desired direction. multi-modes operation. So here I can talk about TA and TM modes, and also about vertical and circular, vertical and horizontal and circular polarization. Okay, so if I have array antenna that function for these three polarization and TO and TM mode, so it's better than array antenna that function just for one mode. Okay, so the last challenge I talk about multiple frequency bands. So I talk in configuration for multiple frequency, and also we can talk about multiple frequency bands. So if I have array antenna that function for a multiple bands is better than array antennas that function just for one band. Okay, so these are some challenges in designing branched array antennas. If you have any question about array antennas, branched array antennas, microstrip or patch or coplanar array antennas, you can contact us in our YouTube channel or on our Facebook. Okay, so see you in other video and other subjects.